Võ Hữu Hiệp, and today I will present my senior design project and application of deep learning for self-driving cars. So my presentation will be divided into 5 chapters, and the first chapter is the overview of the project. So in this project, I use one scale model car built based on the wheelchair tracer platform. With the brand of the car is the Nano developer kit, and to keep the car lightweight and cost effective, I use only one wide-angle camera as the only vision sensor. And for the testing environment, I design a flat number 8 track with featuring a white floor, black land boundaries on the sport side, and yellow dotted line in the center. And to simulate the real-world driving scenario, I program the car to recognize and obey 11 different kinds of traffic sign class. Some of them will have immediate action, such as slow down, stop, turn left and right, and some of them will only give information without any action, like no stop. And moving to chapter 2, problem statement and research significance. So the core problem of my project is the fact that running multiple deep learning deep learning models on limited resource device such as this nano can result in a very bad performance, only ranging around 1 to 5 FPS. So it would be very dangerous when applying to real-life driving scenario. So the significance of this project is to prove that by effectively optimizing the deep learning models and by creating a smart architecture, we can have multiple deep learning models with the inferior speed high enough to apply to real-life driving. And with that ideas in mind, there are 3 main objectives of this project is to design a vehicle that can follow the road, recognize traffic signs, and obey the traffic signs regulations. Moving to chapter 3, hardware and project executions. Firstly, you can see in this architecture, the main processing unit of the car is the Nano. For the sensor block, I use one camera as to capture the raw image frames, and for the communication block, there is a Wi-Fi module that allows me to establish a connection between my laptop and the car, so I can send the run command to the car and receive the live camera feed from the camera. And when the deep learning model finishes process the image, it will send digital signal to the motor drivers and the subcontroller to physically drive the car. And there are 2 main mechanism of the car is the driving mechanism performed by 2 DC motor on the rear and 1 servo motor on the front to perform the Ackermann steering geometry. And now for the lane following model, to teach the car how to stay inside the lane, I manually ride the car around the track, and at every frame I click the coordinate that I want to take the car. That when you see this exact frame, you should give me this exact coordinate. So the output there is the combination of the frame and the XY coordinate. And for the training of this lane following model, which is based on the ResNet neural network model, it is trained directly on the Nano using a Jupyter notebook program. And then for the sign detection model, I also ride the car around my route to capture the image of the traffic signs, and then I combine my dataset with the online image to further make my dataset become more complex and precise. And for the training of this sign detection model, because I chose YOLO version 8 models, and it has huge computational power. It requires a huge computational power. So the image, the traffic sign image, which is already augmented, will be transferred to Google Colab and trained using the cloud GPUs. And to the chapter 4, model implementation and control algorithm. As you can see in this architecture, there are 3 main components. It is the ResNet 18 models for the lane following task, the YOLO models for traffic sign detection, and the state machine. So to balance the workload of the car, every frame, the ResNet 18 for lane following model will be called out to ensure a smooth and continuously steering of the car. And to save some power, only every 8 frames the YOLO model will be called out to save the GPU resource. And when any traffic sign is detected, the state machine will take over to control the car. And for the lane following task, for the continuously lane following task, after the ResNet 18 model for lane following is being called out, it will calculate the XY coordinate continuously, and the X coordinate will be used in this formula to calculate the angle of the car. And for the traffic sign detection model, the traffic sign to prevent any unwanted detection, the traffic sign must go through several filtering conditions before it takes action. I will explain this one. So, for the traffic sign, it has to be covered at least 2.5% of the total frame, and its confidence must be over 75%, and the RU value equals 0.15. And the center of the body box of the traffic sign must lie between a blue trigger zone, and also the signs must be detected at least 3 consecutive frames before it takes action. And for the state machine, it has many steps, but the main idea is to translate the traffic sign detection into the corresponding throttle and steering value. As you can see in this table, for example, stop sign and red light will force the throttle to be 0, and the steering condition will stay as its current steering angle. For slow down sign, it forces the throttle value down to 0.2. And for the left and right side, we'll have a different approach. If the car sees the turn left or turn right side and it reacts immediately, it will turn before it's actually go into the intersection. So to counter that problem, I designed the program to let the car, when it detects the turn left or turn right side, it will continuously driving for half a second, and then the three-phase, it continues driving for half a second to actually enter the intersection, and then the three-phase turning will be applied. In this three-phase turning program, the phase control, the phase command, and the ResNet 18 lane following model will share the control the car for different throttle speed and steering bias. And after the three phase is completed, the control of the car will be given back to the lane following model to continuously driving the car. And moving to chapter 5, conclusion, limitation, and future work. As you can see in this table, after optimizing the raw models with TensorRT engines, the ResNet 18 models for lane following tasks can reach around 40 FPS. The YOLO model yields around 12 to 15 FPS. However, the actual FPS of the YOLO model, as I mentioned earlier, the A frame, after A frame it will be called out once. So the actual FPS of the YOLO model would be 5 FPS. And this is video. This would be a video about the car state consistent. As you can see in this image, I tracked the trajectory of the car, proving that the car stay within the lane consistently. And for the evaluation of YOLO model, for the loss graph, you can see smooth and downward trend of the training loss, proving that the model learned correctly. And for the confusion matrix, you can see a very strong diagonal line indicating that there is a high prediction accuracy of the model to predict 11 different classes of traffic signs. And as you can see in this video, the car stay right by itself, stay inside the lane and obey the traffic sign regulations. So to keep the time, I will move to the next part. To highlight some specific behavior of the car. For example, this graph, so when the car sees a stop sign, the throttle value drops down to 0 for around 2.3 seconds before continue driving to mimic the real life driving when seeing a stop sign or slow down signs, it correctly drops the throttle value down to 0.2. And for the left and the right side, you can see the three-phase executions, correctly turning the car to the different lane. And although the success of the project, there is some limitation, and there is also some future to encounter this limitation. There is also some future work that can be applied. And in conclusion, based on the result that I have demonstrated today, the three with the buffer work that I have done to achieve the objective, the three main objective of the project, to design a vehicle that can follow the road, recognize traffic sign, and obey the size regulation, have successfully completed. And that is the end of my presentation, and I'll be happy to answer your questions.
Thank you. The video lesson some comments. First, the lesson you were written somehow is written and graph to simulate to evaluate the graph for evaluation for us. Yes. But anyway, your model work with and follow the trajectory good. I had two questions for you about the assembly time also. Sometimes when you increase the speed, the car increase speed, and your algorithm can detect the traffic light, or I don't know, the controller has problem, so it turn instead it turn right, it go ahead, or it turn left. So how to improve your algorithm or increase your method? And the second question about the assembly time for controller. So as I know, you don't control the speed of the motor. You just put the overload, right?
Yes, that's correct.
So when first of all, this is the road. When the road increase the friction, friction, you know friction.
Friction.
Yes, increase the friction. So the wheel will reduce. So how to control exactly the turn left or turn right?
So the first question is that you mentioned that the processing speed of the car might sometimes miss the, for example, miss the sign. It cannot see the sign, or it see but it cannot react immediately. So to counter this problem, for the speed of recognizing the signs, as I mentioned earlier, I pointed out every 8 frame because according to the speed, you can see it's really slow, so I pointed out every 8 frame to save the GPU's resource in the car. So if I increase the speed of the car, I might point the yellow, the sign detection models out more often to encounter the speed increase. And for the second question, when increase, for example, the track increase the frictions, it's surely because I use an open loop control of the motor, so any friction or example any dynamic loss like a backage on the car will slow the motor down. So in my understanding, to counter the friction, I will increase because the power of the car, I control the speed by telling it to work how many percent of the actual RPM. Like for example, the motor RPM is PSI is 333 RPM, so I only is now 30% of the power. So I can try at this speed to encounter the friction. I think the direct.
How do you know the friction to increase the BW?
By calculation.
Calculation what?
Sorry. There is. Sorry, I will answer my questions again. There is an DID. There is an encoder on the motor, so there is definitely can make a DID value to control the car. So I think that
Yes, you have to include the BID controller for speed.
yes. So
If you don't have the
I
BID
think that is
controller for
the
speed,
direct fix to encounter the friction, because this is only an open loop system, so the value is not considered.
When you want to deal with the friction, what kind of control signal you send to the motor?
Sorry, friction.
Yeah, well, when you want to deal with the friction or centrifugal force or gravitational force, what kind of control signal you send to the motor?
do you know the motor? What is the input and what is the output of the motor or motor model?
I see. I studied that, but right now I forgot.
DC motor?
Yes.
How to change speed the DC motor speed?
You
How to change
the signal.
No. Just,
I change
the motor. You don't have any controller. Now you have the motor, right?
Yes.
How to increase the speed of the motor?
With the corresponding voltage.
Yes. You increase the voltage.
Voltage.
But when you control with friction, you have to control what?
Friction.
Yeah. You, for example, when you had load 2% different, 1%, 2%, 3% sit on the car, right? So the weight is heavy. So what is the input to put the car go with the constant speed? What kind of input?
The torque speed.
Yes, right. You have to increase the torque.
Okay.
Another thing.
Small question. Have you tested in the different light condition?
Yes. For I tested in the morning, like 8 o'clock to 10 o'clock, and also I also collected the data for at night, but with the light directly hitting from the ceiling down. Not this is from the natural sunlight which goes diagonal, and I also tested that I also collected the data when I drive the car at 5 p.m. without light from the ceiling, and at 6 p.m. with the light from the ceiling. So also the collected data for lane cooling is also augmented for different brightness. So it's set when it goes in complete darkness, it can follow the light in different lighting conditions.
And the other question is in real life there are many objects with the side signal or the visualize your side that you detect. So that how do you recognize in not the side
So your question is if anything that is not the traffic sign or
Yes.
some other traffic sign, would it detect or not? The answer is it will not detect because it's not object detection data is not included in my training. So if I want to, it is also a future implementation for training for more general traffic vocabulary. For example, if I want it to recognize the speed limit, the size like 60 kilometer speed limit, I need to I need to collect the more data of those traffic signs and retrain the models to recognize those. So if the traffic sign there is not be in my data set, it will not recognize.
Okay.
Thank you.
Thank you so much.